more, but today I will do connectedness and all. So, okay, let us start. Okay. So in the first lecture, we defined dense subsets of matrix spaces, and we proved one equivalence of denseness using the open sets. So we will take that equivalence to be a definition of dense sets in a topological space. So definition: dense sets. So X is a topological space, and A is a subset of X. Then we say that A is dense if for every open subset U in X, A intersection U is non-empty. This is the equivalence that we proved in case of metric spaces, and we are taking this as a definition of dense sets in a topological space. Fine. Some more definitions, and we will see some equivalences, and then we will start with connectedness. Okay. So just for the sake of an example, Q as a subset of R in the Euclidean topology is dense. Because you take any open set, it will contain a rational number. That is why Q is dense in R. Fine. Another definition.
Excuse me.
Yes.
Actually, I had a question regarding the previous lecture.
Okay.
So, can you please give me an example of a space which is not housed-or?
A space which is not housed-or. Okay. So for that, non-housed-or. So Vedanta proved that this set, this collection of subsets, is a topology on X. And if say X is not empty, and say X is not empty, let's say it has some, say, greater than or equal to 2 elements. Okay. Then pick those elements A comma B in X. Then there does not exist any open set which separates A and B. Like there does not exist any U V open such that A is in U, B is in V, and these are disjoint, because the only open sets that we have are empty and the full set. So this is an example of a non-housed space. So is it okay?
Yeah, thank you.
There are few more important Hausdorff spaces which are very important, but like in algebraic geometry, there is a Zariski topology which is also non-Hausdorff, and these are of very much importance. Okay, fine. So we will go ahead, and I will give you one more definition. Closure. So let's A is a subset of a topological space X. Then closure of A, which is denoted by a bar over A. This is defined to be intersection of all closed subset C which contain A. A is contained inside C and C is closed. So one inference that we can make directly from this definition is that because in arbitrary intersections of closed sets are closed, therefore A closure is also a closed set. This is a closed set. Okay. Now I want to give one more characterization of this closure. So I think Vedanta defined limit points in the previous lecture. So we will use those to give an equivalent definition for these claim. The claim is A limit points of A. Limit points of A. And the proof is not difficult. I will just give a sketch of the proof, and I want you all to complete the proof. So as a sketch, I will try to. So you all should notice first that A union this set limit points. This is a closed set. You should show this first, and you should also try to prove that any closed set contains all its limit points. These two things are not difficult to show, and if you show these things, then from the definition of the closure of a set, these two sets become equal, because A union limit points of A is a closed set, and each set contains the limit points of A. Each closed set containing A contains the limit points of A. So I want you all to complete this proof. Is the idea clear to everyone, or should I elaborate it more? I guess it should be doable. Is the idea clear to everyone, or else I will proceed?
Yes, yes, clear.
Okay, fine. So another equivalence of dense sets that I would like to give you in terms of closures is this. I guess this is also easy. I just want you all to do this homework. A is dense in X if and only if A closure is equal to A, is equal to the full space X. So this is an easy thing to verify. So I think you all should try this one. Fine. The next thing that I want to do is like some simple things only. Okay. So like if you have a continuous function, continuous function f and g such that they agree on a dense set such that f of x is equal to g of x for all x in A, and A is a dense set, that is its closure is the full set from the previous homework. Then what we can say is f and g are equal. So if two continuous functions they agree on a dense subset, then they must agree everywhere. This is like analogous to the case of reals, where if we have a continuous function on Q that has a unique extension on a unique continuous extension on R. So okay, this happens when the okay, let f and g are maps from say x to y when y is Hausdorff. I should be able to separate the points. In this case, the continuous functions they agree everywhere if they agree on the dense sets. Okay. So proof of this. Okay. So by the homework that I gave you, A closure is equal to X. Now f and g are, these are functions from x to y, and y is Hausdorff. Okay. Let us say so both of these functions agree on A. Say they don't agree on some, and this A closure, this is A union the limit points of A. Limit points of A. So they f and g both agree on A. Now we want to prove that they agree everywhere. So say they don't agree. Say g of x is not equal to f of x for some x outside A, because on A at least they agree. Then these two are points in Y. These two are, so fx gx, these two are points in Y. Since the space is Hausdorff, I can find open sets U and V which are disjoint and contain f of x and g of x respectively. Okay, and by the continuity of f of x, by continuity, the pre-images of these open sets, these are also open. So f inverse of u is open, and g inverse of v, these two are open. Okay, and by the definition we have that intersection of two open sets is also open. This is also open, and x is contained in both of them because f of x lies in u and g of uh, yeah, so f of x lies in u and g of x lies in v. Therefore, what am I saying? Yes, yes. Okay, fine. So x belongs to u. Sorry. So f of x belongs to u and g of x belongs to v. Therefore, this statement holds. So basically, we have a non-empty open set inside X. So F inverse U intersection F inverse V. This is non-empty open set in X. Therefore, by the denseness of A inside X, this open set must contain a point of A. Therefore, by
That is intersection G inverse V, right?
sorry, I didn't get your question. Can you repeat?
That will be F inverse of U intersection G inverse of V.
Oh yeah, really sorry for that. That should be G. Yeah, exactly. G inverse of V. Fine. So by the denseness, we have that there is some point of A. There exists A in A intersection F inverse U intersection G inverse V. Fine. So what does this mean is that F of A, this is in U, and G of A, this is in V. But the hypothesis of the statement was F and G agree on A. Therefore, these two quantities, they are equal. Therefore, f of a, which is equal to g of a, belongs to u intersection v, which is a contradiction to the fact that we had u and v disjoint at the beginning. So our assumption that they do not agree at a point outside A is wrong. Therefore, the statement follows. There is a unique continuous extension of functions which are continuously defined on a dense set to the full space. Okay. So, for example, it can be said that Q2 continuous extensions to R, these are also unique because Q is dense in R. And this fact is used, you might have used this fact in functional equations and all, Olympiad problems or something. Okay. So these are some of the things that I wanted to cover. Now I will get into connectedness. Connectedness. So, as far as the definition is concerned, okay, I will define a term. So, X, a topological space, it is said to be disconnected. It is said to be disconnected if there exist two open sets U and V which are disjoint, so that their union is the full set. U union V, this is the full space. So I am breaking the whole space into two open sets, U and V. So if such a disconnection, this is called a disconnection of X. So if a disconnection exists, we say a topological space is disconnected. And the negation of this statement, X is called connected if it is not disconnected. If it is not disconnected. So there does not exist any pair of disjoint open sets such that their union is the complete set. So I would like to give some examples over here. Okay. So I will give some examples. Say X is equal to close 0, 1, union 2, 3. So I am viewing this set X as a subspace of R with the usual Euclidean topology. Okay. So these are 0, 1, 2, 3. Okay. Now 0, 1, this thing is open in X. Can someone, is it clear to everyone, or that this subset of X is open?
Yes, in the subspace topology, right?
Yes, definitely. So even if you view this as a metric space, this thing will be open. So this the topology, the subspace topology, and if you restrict the metric to this subset, and then take the topology, both of those things are same. So you can view it in both the ways. So this is open in X. So subspace topology, and similarly 2, 3, this is also open. And clearly these two are disjoint and their union is the full space. So this is an example of a disconnected disconnected topological space, which can be seen easily in this case, that there are two disjoint pieces. Okay, so this is a non-example, and now I should give one example as well. Another example. 0, 1 as a subset of R with the usual topology is connected. Okay. So fine. Let's say this is not connected. Then by the definition of a disconnected topological space, there exist open sets U and V, such that their union is the full space. Okay. Now what I will do is I will define a map F from 0, 1 to R, so that F restricted to U it is 0, F restricted to V it is 1. So on U it is 0 and on V it is 1. The point is this map is continuous. Can everybody see that this map is continuous?
Yes, because even we are open sets.
Exactly, because U and V are open sets. So if any open set in R contains 0 and 1 both the points, then pre-image is the full set. And if it contains individually, then since U and V are open, therefore pre-images are also open. So this is a continuous map. But in real analysis 1, you might have studied that this continuous map from 0, 1 to R. So by the intermediate value theorem, there must exist some point in 0, 1 whose value is say 1 by 2, because this lies between 0 and 1. But we don't have any point in 0, 1 whose value is 1 by 2. So this construction contradicts the intermediate value theorem. Therefore, this is a contradiction to IVT, the intermediate value theorem. Therefore, the set 0, 1 it should be connected. Fine.
I did not understand this construction and why is it continuous. Can you explain that?
Yeah, sure. So this map. So by the definition of continuity, we have to what we need to check is that any pre-images of open sets are open. So if any open set, say like this, if it does not contain 0 or 1, then the pre-image is empty, which is open. If it contains exactly one of these points, say like 0, if the open set contains exactly one of the points, then the pre-image F inverse of that whatever open set, it will be U. But U is an open set. Therefore, pre-image is open. Similarly, for 1, if any open set contains just the singleton 1 and does not contain 0, then pre-image of any such open set is again open because the pre-image is V. And if any open set contains both 0 and 1, then the pre-image is the full set 0, 1. So this map is definitely continuous. Is it okay?
Okay.
Yeah, and by the epsilon delta definition of continuity, like epsilon delta definition and this definition that we are using right now, these both are equivalent in the cases of metric spaces. We proved in the first lecture, and therefore that definition gives rise to a theorem the intermediate value theorem, which says ki if we have 2 points, 2 distinct points, then any point in between should also be in the image. But in this case, we don't have say 1/2 in the image of this continuous function. So that is a contradiction.
Okay.
Okay. So this
Excuse me,
construction contradicts the intermediate value theorem.
I had a
And
question.
yes.
All of this stuff we are doing it in the subspace topology, right?
Subspace topology of 0, 1, yes. Okay, was that the question or something else?
Yeah, I was thinking like we are doing it in the usual topology, but then 0, 1, how would that go?
Can you repeat? I didn't get your question. Like your voice is bit inaudible. So
You said 0, 1, it's open, but with topology it's not possible.
see my topological space X over here is this set 0, 1. So view this as a metric space, or you can view this as a subspace of R.
Yeah,
Both are
I was
equivalent.
viewing in that way.
Okay, what is your question?
I just said that I was viewing in that subspace topology subset of R.
Yeah. So even if you take subspace topology, and the topology will be same. Even if you consider this as a metric space also, the topology will be same. So take that as a homework. You could try that. Okay. Yeah. So I should actually write that once. So if say X is a metric space and hence a topological space, and Y is a subset of X, then the subspace uh, subspace topology on Y, subspace topology on Y, this is same as the so we can view Y as a, then since it is a subset of a metric space, so Y itself is a metric space because we have a notion of distance between any 2 points of Y, and therefore it is also a topological space in that respect. So in both the respects, these are the topology on both of these sets are same. Subspace topology on Y is same as the metric topology on Y. Metric topology on Y. So you should check this thing. It is not very difficult to see all these things. So is this clear to everyone now?
Yes.
Fine. So I will go ahead. Theorem. F is a continuous map.
Can you please show the previous part once again?
Yes. This one or
Yes.
huh,
Okay. Thank you.
fine. So if F is a continuous map from X to Y and X is connected, then F of X, that is the image of X under F, is also connected. This is also very easy to see because say F of X is disconnected, then F of X, we can write it as a union of two disjoint open sets. Then if we take the pre-images, F inverse of U and F inverse of V, these two will be disjoint these two are also disjoint, and since U union V is the full image of X under F, therefore F inverse of U and F inverse of V, these two sets also should have the union as full X. F inverse of U union F inverse of V, this should be equal to X. So if we have a disconnection of F of X, we also have a disconnection of X. Therefore, if X is connected, we must have F of X also connected. Is this clear to everyone?
Yes.
Okay. So I would like to show you one more way to check connectedness, that is an equivalence of connectedness. So I will an equivalence. So X topological space is connected if and only if every continuous map F from X to the set 0, 1. This set is with discrete topology. Any such kind of a continuous map is constant. So can someone explain why is this true? Is the statement clear to everyone?
Yes.
Okay, so I will try to give a proof of this. Say like okay, so say X is connected. So I would like to show that every continuous function is constant. So let's say F is continuous but not constant. Okay. Therefore, there is some X in X and Y in X such that F of X is 0 and F of Y is 1. And but with discrete topology, this set has 0 and 1 singleton sets as open sets. Therefore, by the continuity of F, their pre-images are also open. This and F inverse of 1, these are open, and their union must be X because there is no other space to go. So F inverse of U union F inverse of 0 union F inverse of 1 is X, and both of these are non-empty. Okay, and by continuity these are also open. Therefore, X is disconnected. This is a contradiction. Therefore, any continuous map should be constant. Any continuous F from X to 0, 1 with discrete topology is constant. And for the other way, what you can do is, so we have every continuous map constant. Now say X is disconnected. say X is disconnected. Therefore, I can write X as union of U union V, where U intersection V is where U intersection V is empty and U and V are open, and define a function f from X to discrete 0, 1 such that f restricted to U is 0, f restricted to V is 1. And by the similar argument that we did before, this map is continuous. But our hypothesis was that every continuous map is constant, but we have constructed a continuous map which is not constant. Therefore, the assumption that X is disconnected must be false. Therefore, X is connected. So, continuity can also be seen from this equivalent definition that every continuous map from X to the set 0, 1 with discrete topology is constant. Okay. Is it clear to everyone?
Yes, it's clear.
Okay. So, I would like to show some interesting things, but before that, I would like to do these important things. So, one more theorem. It says that if C, okay, so I should define this thing first. So, definition: a subset of a topological space X is called connected if it is connected in the subspace topology. Connected in the subspace topology. Okay. So this gives you a way to assign connectedness to subsets of a topological space. And now I would like to give an important result, which is that if C is a connected subset of a topological space X, then
Could you show the last definition once more?
yes. So earlier we defined connectedness just for like topological spaces. Here we are extending the definition to the subspaces of a topological space by using the subspace topology of the original set. Okay.
Okay, but how can this be a definition? Shouldn't this be a claim or something?
So we define connectedness just for topological spaces. So to talk about connectedness of subsets of a topological space, we should have a topology on that subset. So which topology to consider? This is what I'm telling you. So this is the definition of that.
Okay.
Yeah. Like you need to have the subset as a topological space, right? To
Yes.
talk about continuity, because we defined it in that way. So what I'm saying is I will call it connected if it is connected in the subspace topology given by X. Okay.
Okay.
Yeah. So fine. So I have a connected subset, like, so here C is connected as a topological space, and the topology is inherited from X by the subspace, which we call as a subspace topology. So if C is connected subset of X, then C closure that we defined at the beginning as the intersection of all closed sets containing C, or with, or like C union limit points of C is also connected. Also connected. This theorem is important because you can uh, check connectedness of some peculiar subsets just by using this thing. I will show you some examples of this. Okay, so let me try to prove this. So okay, I will show you one more important result before this. So let me write it as lemma or something, which is like kind of easy to see also. So if you have A is connected subset of X such that A is contained inside U union V, where U and V are open in X and they are disjoint, then this A either belongs to U or it belongs to V. I think this is pretty easy to see. Can someone tell me why this should be true?
If we assume not, then that will violate the connectedness of A, I guess.
Yeah, yes. So if it had non-empty intersection with both, then it will contradict the connectedness of A, because open sets in A looks like open sets in X intersected with A. So I will just write it quickly. So if not, then A intersection U and A intersection V, these sets are open. These sets are open in A, and if A intersects with both A and B, then both of these are non-empty also, non-empty. Therefore, this gives a disconnection of A, hence contradicting that A is connected. Fine. So, okay. So I will give a proof of this theorem. Proof of the theorem. So we wanted to show that we are given that C is connected. We wanted to show that C closure is also connected. Suppose it is not, then C closure can be written as U union V, where U and V are disjoint, but C is connected and C is a subset of the closure by the definition. Therefore, C will belong to one of these. Say C is a subset of U. But then, since U and V both are non-empty, so V must contain some limit point of C. Therefore, there exists limit point A of C in V. Otherwise, V becomes empty. So there should be some limit point of C which lies in V. But therefore, A belongs to V. But C is contained entirely in U, and therefore this is a contradiction to the fact that A is a limit point. Therefore, A can't be a limit point. Can't be a limit point. Okay. So this is a contradiction. Therefore, C closure must also be connected. C closure must be connected. Okay, should I go over the proof once, or is it clear to everyone?
Can you once repeat it?
Can you repeat yourself?
Can you please repeat it once? I couldn't hear all of it.
I am unable to hear you. Your voice is a bit hazy.
Can you repeat it once? I couldn't hear all of it.
Are you asking me to repeat?
Yes.
Okay, okay. So whatever hypothesis was that C is connected, and we wanted to show that C closure is also connected. So we said that, let's say it is not. So U and V. So there exist open sets U and V, both of which are non-empty. U V non-empty, empty, such that C closure is the union of these two. But then C is a subset of C closure, and therefore C is a subset of U union V. But in the lemma, we prove that in such a case, a connected set must lie in one of the open sets. So what I said is, let's say C lies entirely in U. So C closure is equal to C union the limit points of C. Okay, C closure is this, but C lies entirely in U, and we know that V is non-empty. Therefore, V must contain the limit points, at least one limit point it should contain of C. Therefore, there exists a limit point A of C, which is in V. Okay, but then what is the limit point? For A to be a limit point, any open set which contains A, it must intersect with C. But since C lies completely in U, and U is disjoint with V, therefore C intersection V is also empty. Therefore, A can't be a limit point. A can't be a limit point. And hence this contradicts the fact that V is non-empty, or whatever. Yeah. So is it clear now?
Yes.
Okay. So C closure must also be connected. So if C is connected, then C closure must also be connected. You can prove this using the things that we did earlier also, like extension of continuous function to, okay, I will just give you an idea of another proof. So we wanted to show that C closure is connected. So basically what we want to show is that any continuous function from C closure to the set 0, 1 with discrete topology is constant. Now restrict this function to C, but C, because of the connectedness of C, this function restricted to C is constant, and extension of a constant function. Now C is dense in C bar. This thing I gave you all as homework. So C is dense in C bar. Therefore, the continuous extension of this thing must be constant, because constant function is continuous and the extension is unique. So this is another idea. You can prove it like this also. Okay, so work it out. Okay, is the idea clear? So this is just the same thing said in other words. Okay. Uh, is this clear to everyone till this point?
Yes, it's clear.
Okay, so I will proceed. So one very natural result which one should expect is that if I have a topological space X and I have few connected subsets of it which have say some intersection, then their union must also be connected. So this is a result that we can show. So the theorem is, if we have a collection of connected subsets, say Ci I in some indexing set I is a collection of connected subsets of X. X is a topological space such that they have non-empty intersection. This is non-empty. So we have few open sets which have some non-empty intersection. Therefore, in such a case, then we must have their union is also connected. Okay. So this is also easy to show if we refer back to the lemma that we proved earlier. That okay. So we will use this lemma. So proof, say union Ci is equal to U union V, where U union V, these are sorry, U intersection V are is disjoint. U and V are disjoint. Then okay, now Ci is a subset of this. Therefore, each Ci must belong to one of these by the connectedness of Ci's. Therefore, Ci belong to U or V entirely. I should write it like this. Ci is contained entirely in U or entirely in V. Now, now say for some I, Ci is in U, for some I, then all the others should also lie inside U because they have non-empty intersection. Therefore, for Cj can't lie this. This can't be in V, otherwise Ci intersection Cj, this will be empty. But we had an hypothesis that we have non-empty intersection between any sets over here. Therefore, Ci union is contained. All of them must lie entirely in U. So therefore, we can't have any disconnection. Therefore, we can't have a disconnection. Therefore, the proof is done. This is connected. Is it clear to everyone? The crucial fact here was the fact that intersection is non-empty. Is this
Yes.
clear to everyone?
Yes.
Okay. Now, it's already 10. So I will go to path connectedness now. So,
I didn't get what the contradiction was in the last theorem.
okay, so basically, if we had any non-empty sets like this, then each of the CIs must, like the union must lie entirely in one of them.
Okay.
So other one has to be empty. So we can't really have two non-empty open sets whose union is this thing.
Okay. Okay.
Yeah. So you can view, you can say it in terms of contradiction also. Same thing. Okay, is this clear now?
Yeah.
Okay, fine. So okay. So I will define path connectedness. This is like more natural than the connectedness that we defined earlier. Path connectedness. This is more natural. So like just to give you an example, say we have R2. Then between any 2 points, I can have a continuous curve like this joining any 2 points of R2. So when such things happen, we say that the space is path connected. I will define it precisely now. Okay. So we need to define notion of paths first. So these are in some sense one-dimensional objects. So like I can number them from 0 to 1 continuously in some sense. Okay. So like 0, 0.3, whatever, 1/2 and 0.9. So this is a stretching of the 0-1 interval. Okay. So path is nothing but a path is a map, a continuous map f from close 0, 1 to x, which is a topological space. So this is a path, and we say that f of 0, say it is some point a, and f of 1 is b. Then we say that this is a path from a to b. So this is a definition of a path from a to b. Is the definition clear to everyone?
We are calling the mapping to be a path or the image under the map to be a path.
Yes. So we are calling the map to be a path. So
Okay, but
that
the
picture.
same image can have different types of parameterization, so we will call them different
Sure.
paths.
Yes. Same. The same image may have different functional forms, but existence of a map is enough because it will give a continuous image in some sense. So we are calling the function as a path from A to B and not the image. So path is a map. Is it clear now?
Yes.
Okay. So this is like more natural than the previous thing. Now, a topological space X topological space, it is called path connected if for every point a comma b in x there exists a map f from 0 comma 1 to x, with that is there exists a path from a to b. So there exists a map from 0 comma 1 to x continuous such that f of 0 is a, f of 1 is b. So R2, for example, is a path connected space because I can join any 2 points with a straight line, and by that I mean if a comma b belong to R2, then consider this map f from 0 comma 1 to R2. Example such that f of f of t is equal to a plus b minus a t. So this is a continuous function whose such that f of 0 is a and f of 1 is b. So for any 2 points of R2 I can find a continuous map like this. Therefore R2 is path connected. You can also draw some peculiar paths, but this works. Okay, so we should have some connection between the two kinds of connectedness. So it turns out that the connectedness that we defined earlier is a weaker condition than path connectedness. So connectedness is weaker. This weaker is in logical sense than path connected. Okay, so what this means is that path connected implies connected. That is, if x is path connected, then x is connected. Okay, is this clear to everyone till this point? Yes.
Yes.
Yes. Okay. So, like visually, you can think of this result that I wrote over here like this. So, like let's say like this is what x looks like, and if I have some point, then I have paths from that particular point to every other point. Okay, and we prove that okay, I should not tell this at this point of time. Okay, I will tell it at a later. Okay, I will prove it and then I will tell you this. Okay, so proof. So say x is disconnected, then what do we have? We have u union v, u intersection v is empty and u and v non-empty. Okay, but the space is given to be path connected, and since u and v these are non-empty, I can find a point in u and a point y in v, and by the path connectedness of the space, there exists a map f from 0 comma 1 to x such that this is continuous and f of 0 is equal to x, f of 1 is equal to y. So this kind of looks like this. I have, this is u, this is v, and I have some sort of a path over here. But then f inverse of u, because u is open, this is also open, and f inverse of v, this is also open, and the union is exactly equal to 0, 1, and these are non-empty. Why? Because x belongs to this and y belongs to this. Therefore, if we assume that x is disconnected, then we get that 0, 1 is also disconnected. But we proved earlier that this is a connected space, so this is a contradiction. Therefore, path connectedness always implies connectedness. Every path connected topological space is a connected topological space. So what I was saying over here with this picture is that, like, if you have a point x, some point x over here, then for any other point you can find a path, and path is a continuous image of 0, 1. Therefore, this image itself is a continuous subset of x, and all of these continuous subsets, they have this point x lying in their intersection. Therefore, and union of all these images is obviously x, so x must be connected. So just a visual way to think about it, nothing else. So is the proof clear to everyone? Okay. Am I audible? And like, am I audible to everyone?
Yes, you're audible.
Oh, okay, fine.
Yes.
Yeah. So is the proof clear? So I will proceed further. Okay, fine. So there are certain examples. I don't think we have too much time left for completing those things, but I will at least I will mention
One
some
minute.
examples.
Sorry.
Yeah.
Why is F inverse U union F inverse be the entire 0, 1 space?
Okay. So we are mapping every point of 0, 1 to some point in x, and
Yes.
x is the union of u and v. So u and v like saturates the full space. Okay.
Okay.
And so like, so everything, every point of 0, 1 goes to either u or v. So their pre-images must contain all the points of 0, 1.
Right. Okay.
Yeah. Or you can think like set theoretically, f inverse u union f inverse v. This is equal to f inverse of u union v, and u union v is x. This is what I was saying. And since this is a function, this is equal to 0, 1.
Yeah. This makes more sense.
Yeah. Yes. So fine. So there are examples of connected sets which are not path connected. So this direction is not true, but we don't have too much time to cover this, but I will mention those things, and I think we will stop after that. So okay. Mhm. Connected does not imply path connected. Okay. So okay, let me try to draw a picture. So this is R2 and this is 1, and I'm making these lines joining 0, 0 to 1, 1 by n. N is a natural number. I'm making all these lines. Okay. So now if you think, if we take any 2 points over here, so our set is this. So if I call the line joining 0, 0 to 1, 1 by n, say Ln, this is the, so this is L1, this is L2, and so on. So my space is this, x is equal to union Ln, n from 1 to infinity. So this is the topological space that I'm considering right now. So if you take any 2 points, then those 2 points must lie in one of the lines. If they lie in exactly the same line, then clearly they are path connected. If not, say these 2 points lie in some different lines, then we can go to 0, 0, and then we can get back to the other point. So this is a continuous map. You can try to write the functional form, but I don't think it is necessary to, like, it is clearly a continuous map. So this set is clearly a path connected topological space. Okay. If I add the x-axis also, this line. So if you think any point in, say, I will call this line, say L infinity, which is the set of all points in, like, of this form, x, 0, so that x less than equal to 1, greater than equal to 0. Say y is equal to x union L infinity. Then from the same arguments that I gave earlier, y is also a path connected space. Okay. Now all of these points that I had over here in the line L infinity, these are so let me draw this picture once again. Okay. So any point in this line L infinity, if I restrict this, so this point, this point, this point. So if I take any point a, 0 in L infinity, then these points that lie in Ln of which have some x coordinate a, I don't know what will be the y coordinate, you can calculate that. So these points, the limit of these points is this point a comma 0 in L infinity. So what I'm basically trying to say is this point a comma 0 in L infinity is a limit point of x. Okay, is this clear to everyone? Like I was a bit vague over here, so is this clear to everyone?
Yes, yes.
Yes.
Okay, fine. So you can check that y is actually the closure of x. Like no other point is the limit point. You can check this. So what we can say from the theorem that we proved, that if C is connected, then C closure is also connected. And so basically, if C is connected and I have any set S between C and C closure, then this set must also be connected. Given C is connected, then any set which inclusively lies between C and C closure is also connected. So this is also easy to check. So basically what I'm trying to say is uh, 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 I am and I am, so L1, L2, all these things. I'm not considering L infinity right now. I will just take this point. And from 1 to infinity along with this point 1 comma 0. I will call this uh, what say C. Let's C contain phi, which is using this property is also connected. Is this clear? What I can actually show is, so this point 1 comma 0, the red point, lies some, so it has to jump to say if I want a path between a point in L2 and 1 comma 0, then this point somehow has to jump between the lines. So like it is not contained in any of the lines. So these are heuristics, but this space is actually not path connected, but it is a connected subset of R2 from this thing that we wrote over here. So I don't think we have too much time to show that this is a path connected space right now. So is this clear to everyone? At like why is this connected at least?
Yes, yes. So the
Yeah,
claim is that C is not path connected.
yeah. C is not path connected. Yeah, so that point 1 comma 0 lies in some sense. It is a bit far, but not very far. So this is a limit point, but to make a path, it has to jump somehow. But that it doesn't have that much space. Like so,
Okay.
so it can be shown that this is not path connected, not path connected. You can actually construct similar, like many more examples like this using using this thing. Like you take C to be connected, take its closure, and somehow remove points so that it lies between C and C closure, and so it still remains connected, but it somehow lost its path connectedness. So that is the main idea. You can construct many more examples like this. So showing that this space is not path connected requires some time which we don't have right now. So I think I will stop at this point of time. If you have any questions, you can ask right now. So if there are no more questions, I think we can stop. So like I don't know, like we may have some like there was a very interesting result about topological vector spaces, but I don't know with how many people are going to be interested in that. Okay, like okay, fine. We will see. We will see at that point of time. Even I'm not sure whether I will. Yeah, actually, I had it prepared, but I I thought that connectedness is an important thing to cover, so I did. Yeah, yeah. Okay, fine. Yeah. Okay. Yes. Fine. So
We'll let you know about further lectures. Okay, we'll discuss and let you know.
what? I didn't understood what happened.
No, nothing. Like let's